Let's go ahead and look more carefully at the structure of diazomethane and consider what might be happening under these reaction conditions. And I should tell you that the reaction conditions generally require some light. So we're going to treat diazomethane with light in order to produce a reagent called a carbene, which will cyclopropionate the alkene. Let's take a careful look at diazomethane. It's a very interesting compound. There are numerous different resonance forms that we could draw for diazomethane, but here's one. In this particular resonance form for diazomethane, we have again a dipolar structure, meaning that there's a, in this case, nitrogen atom that's negatively charged and one next door which is positively charged. In another resonance form, we have a negatively charged carbon and a positively charged nitrogen. This latter resonance form is a particularly useful one for us to look at and consider, because it turns out that if we shine light, or even if we heat up this particular diazomethane compound, we can spontaneously extrude nitrogen gas. So if I just break this carbon-nitrogen bond here, placing both electrons onto the nitrogen, then what I get is a methylene compound in which my carbon is bound to two hydrogens, those two right there, and has a lone pair. It's actually neutral. It's a very interesting species. We don't see carbons with lone pairs very often. These neutral species are called carbenes, and this carbene is certainly a big part of this story. But another part of the story is the other molecule that forms, and it is nitrogen, as in nitrogen gas. So when we take this diazo compound and we either heat it up or shine light on it, shining light would be the preferred method, we can extrude nitrogen gas, and nitrogen gas will just simply evolve out of solution, leaving behind this highly reactive carbene. So far in organic chemistry, you've been exposed to carbocations, which are highly reactive intermediates. There are numerous other types of highly reactive carbon-containing intermediates, and carbenes are certainly one of them. We're not going to study a whole lot of carbene chemistry, but it is important for us to understand that carbenes can form from diazomethane, and now we'll see why. If we form the carbene in the presence of our alkene, so there's my diazomethane, which I subject to ultraviolet light to produce this highly reactive carbene intermediate, then this carbene in the presence of the alkene will cyclopropionate the alkene, and it's the reason that I get the cyclopropionation product shown. This CH2 of this new cyclopropane came from the carbene. The aeroformalism is quite simple. Turns out that this carbene has an empty p orbital on it, and so it's a very interesting species. It can behave as both nucleophile and electrophile. The nucleophilic part is the lone pair, which can attack a pi bond. The pi electrons, on the other hand, can bite back down on the empty p orbital in order to produce, in one concerted step, the corresponding cyclopropionation product. So that's cyclopropionation of alkenes. I'd love to be able to tell you that the cyclopropyl group is every bit as useful, synthetically speaking, as an oxirane or an epoxide, but it turns out that this is probably not the case. Cyclopropanes are certainly very interesting. They have lots of angle strain, yet those carbon-carbon bonds are strong enough that it is a persistent species, one that's isolable. It can be purified through recrystallization if it's a solid, or distillation if it's a liquid. And once it's been isolated as a pure compound, it can be stored for long periods of time. So it's not so highly reactive that it's going to fall apart. And because there's no oxygen present, there's no built-in leaving group in this cyclopropane structure as there was in the oxirane structure. So consequently, from a synthetic perspective, it's a little bit more of a dead end. Once we make a cyclopropane through this diazomethane chemistry, we're probably pretty much done. That is going to have to be the end point for most of these compounds. That is cyclopropanation of alkenes. Well, we're almost done. We've only got 2 reactions left to cover, and they're very closely related to each other. One is a Markovnikov hydration of an alkyne. And you know, of course, that alkynes look like this. This would be a terminal alkyne, whereas this would be an internal alkyne. So we have 2 different types of alkynes, and they can both react under these hydration conditions. It's useful frequently to first consider the terminal alkynes because of the different levels of substitution of the 2 carbons of the alkyne. So for example, this is a primary carbon, whereas this is a secondary carbon. So this unequal level of substitution can be useful, particularly when we're talking about Markovnikov processes. Now, let's review very quickly here. Hydration of alkenes. Because we recently learned 3 different hydrations of alkenes. In the first case, we learned that if we take an alkene and we work under standard acid-catalyzed hydration conditions, Markovnikov acid-catalyzed hydration conditions, we will protonate across the less substituted carbon and ultimately add OH across the more substituted carbon to give us this Markovnikov hydration product. On the other hand, if we took this same alkene and we ran a hydroboration oxidation sequence, we would get an anti-Markovnikov hydration product. There's no carbocation involved here, and it's anti-Markovnikov for all the reasons we discussed as we went through the process carefully. Ultimately, because it's anti-Markovnikov, the hydrogen adds across the more substituted and the OH across the less substituted carbons, and so we wind up with this isomeric anti-Markovnikov hydration product. Last, but certainly not least, we learned that if we take an alkene, particularly one that might be prone to carbocation rearrangements, and we treat it with mercuric acetate, followed by a sodium borohydride reduction, we can produce a Markovnikov hydration product in which there is no rearrangement. So in this particular case, we're talking about this product where we've added hydrogen across the less substituted carbon and OH across the more highly substituted carbon, but with no rearrangement. Remember, this is the very same sort of alkene which would have undergone rearrangement under those simple acid-catalyzed Markovnikov hydration conditions. We would get a little bit of this same product I just drew, the Markovnikov hydration without rearrangement, but that would no doubt be a minor product here. The major product would be the result of a hydride shift to the resulting carbocation, a Wagner-Meerwein rearrangement, to give the tertiary carbocation, which will be captured by water, to give the major alcohol product here. So some alkenes are susceptible to these Wagner-Meerwein rearrangements, carbocation rearrangements, and if we want to form a product that doesn't allow for a rearrangement, a Markovnikov hydration product that doesn't allow for rearrangement, then these would be the conditions. Well, that's our backdrop now to understand the Markovnikov hydration of alkynes. I am, as promised, going to use a terminal alkyne since one side is primary and the other side of the alkyne is secondary, or I should say one carbon is primary and the other carbon is secondary. So it's an unsymmetrically substituted alkyne. And it's going to turn out that the best reaction conditions use mercury 2+ reagent, typically a mercury sulfate, in the presence of an acid, typically. And if we do that, we will in fact perform a Markovnikov hydration. Now, let's think about this Markovnikov hydration. We're going to add hydrogen across the less substituted and OH across the more highly substituted carbons. And when we do that, we still have a pi bond left. Because remember, the alkyne, of course, has one sigma bond and two pi bonds. We're reacting across one pi bond to give us this Markovnikov hydration product. This particular product is a special one. You can see that there's an alkene and an alcohol, and it's known as an enol. Now, enols, as it turns out, are very common, and we're going to study them again when we get to aldehyde and ketone chemistry and organic chemistry too. At this point in time, what we need to know about enols is that they equilibrate quite rapidly with their corresponding aldehyde or ketone isomers. Look carefully here at the enol. The alkene pi bond between the carbon atoms essentially migrates here. The pi bond essentially migrates here to the carbon-oxygen bond. So we now have a carbon-oxygen double bond. And this hydrogen essentially migrates out to this carbon such that now I have 3 bonds to hydrogen, a simple methyl group. In other words, the enol is in equilibrium with the ketone. Now, we're not going to go through the detailed mechanism of this equilibration. It's not quite as simple as what I just described. The molecule doesn't toss pi bonds and hydrogen atoms around like footballs in order to equilibrate from an enol to a ketone form. When we get into aldehyde and ketone chemistry and organic chemistry too, we'll go through this in great detail. But right now, what we need to appreciate is that when we form enols, and we will form them whenever we do a hydration reaction of an alkyne, when we form enols, they don't stick around for very long. They equilibrate to the ketones, and the equilibrium generally favors aldehydes and ketones much more so than the enol. So consequently, when we hydrate an alkyne, we're really forming either an aldehyde or a ketone through the intermediacy of the enol, which rapidly equilibrates to the aldehyde or the ketone. Let's look at another one. Okay, here I've replaced the R group with an ethyl, so we're giving this a little bit more of a defined structure, and we're going to treat it with a mercury cation. Again, typically a mercury sulfate would be used to produce the mercury 2+ cation in aqueous solution. And we usually have a little bit of acid present, so we'll use some H3O+ as well. Under these conditions, we're going to do a Markovnikov hydration. We'll add hydrogen across the less substituted and OH across the more substituted. That gives us the enol. But the enol is going to rapidly equilibrate, and the equilibrium will favor the ketone. Once again, the way we think about this equilibration at this stage of the game anyway, is that we simply migrate the pi bond from this carbon-carbon area of the molecule to the carbon-oxygen area of the molecule. So now I've got a carbon-oxygen double bond. This carbon over here is going to pick up that hydrogen, so now I have a CH3, and the ethyl group remains intact. And this is just simply a ketone again. Look at another example. What if I didn't start with a terminal alkyne? What if I started with an internal alkyne, as I have here? 1, 2, 3, 4, 5, 6. This is a 3-hexyne molecule. I'm going to start with this 3-hexyne. I'm going to treat it with the mercury cation, mercury 2+ cation, under acidic conditions. And now, if you look at the levels of substitution, they are identical. There is no unsymmetrically substituted alkyne in an internal alkyne. Both of the alkyne carbons are secondary, so it doesn't really matter where you add the H and the OH, and you would expect that it would add in either direction. There is some symmetry in this molecule, so regardless of which direction it adds in, I'm going to get the same product. So for example, let me just arbitrarily decide that I'm going to add my hydrogen across carbon 3, and my OH group across carbon 4. That gives me this enol, which we now know will rapidly equilibrate or tautomerize to the corresponding ketone. The pi bond migrates to the carbon-oxygen center. There it is. Now I've got a carbonyl group, a carbon doubly bound to an oxygen. The hydrogen effectively migrates to this alpha carbon, alpha to the carbonyl, and I just get this ketone structure. So when you see enols, and when you form enols, recognize that they rapidly equilibrate to the corresponding aldehyde or ketone. So far we've only seen them equilibrate to a ketone, but that's going to change in just a moment. Because now we're going to look at our last reaction, the anti-Markovnikov hydration of aldehydes, of alkynes. And when we do an anti-Markovnikov hydration, we will be able to form aldehydes. Well, before we get to the anti-Markovnikov hydration of alkynes, let us go back and look one last time at the anti-Markovnikov hydration of an alkene. We looked at it just a few moments ago. Here it is. We take the alkene and we perform a hydroboration oxidation sequence such that we add the hydrogen across the more highly substituted carbon, the OH across the less substituted carbon, to give us this anti-Markovnikov hydration product. Well, now we're on to the anti-Markovnikov hydration of alkynes, and we're going to use a very similar set of reagents. Let's go to our alkyne first. Once again, I'm going to choose a terminal alkyne. So this one would be 1-butyne. And I'm choosing the terminal alkyne because of the uneven levels of substitution. Carbon atom number 1 is primary. Carbon atom number 2 is secondary. So when I perform my anti-Markovnikov hydration, which I could use borane to do in a hydroboration oxidation sequence, that is, I could use BH3, but it turns out that there's a bit of an advantage to using a bulky borane where, for example, I have two R groups and only one boron hydrogen bond. Remember, a boron hydrogen bond is transferred, or I should say is an essential part of the transition state in this hydroboration reaction where I'm forming new carbon boron and new carbon hydrogen bonds across this pi bond here. And if I have a bulky organoborane rather than just regular old borane in my reaction with an alkyne, there will be some advantages. I'm going to talk about that a little bit more in just a moment. In the second step, we'd still use the same reaction conditions, hydrogen peroxide under aqueous basic conditions. What I'm going to do here is an anti-Markovnikov hydration. And so, because I'm starting with an alkyne, I'll still have an alkene left over. In the anti-Markovnikov hydration sequence, I'm going to add hydrogen across the more substituted carbon and OH across the less substituted carbon. And now we see the reason for using the more bulky hindered organoborane. When I use the more bulky hindered organoborane, my hydroboration doesn't give rise to a simple alcohol. It gives rise to an organoborane in which the boron is still attached to an alkene portion of the molecule, and that species can undergo further hydroboration reactions. But by using a more sterically encumbered organoborane, I can stop the hydroboration part of the story at the alkenyl stage, which gives me this sort of an enol structure that I've shown here. This enol is very much identical to the other enols we were just looking at a moment ago, except that the OH group here is on the less substituted carbon. So when it equilibrates, remember, the way we're thinking about this, at least for the time being, is that we're going to move those pi electrons, or the pi bond, from this carbon-carbon center to this carbon-oxygen center. And, whoops, I think I messed up, excuse me. We're going to move the carbon-carbon pi bond to this carbon-oxygen center, so I need to draw it appropriately. There it is. There's still an attachment to this hydrogen right here. And this hydrogen we're effectively going to transfer over to this carbon to produce a methylene group, which then becomes part of a propyl. And looks like that. In this particular case, you can see that what we have done is we formed an aldehyde. So this enol, which results from an anti-Markovnikov hydration of an alkyne using a bulky organoborane in the first step, followed by hydrogen peroxide OH-, gives rise to this enol, which rapidly equilibrates to the corresponding aldehyde. Let's look at another example. Here I have a terminal alkyne once again, and I'm going to treat it with a bulky organoborane followed by H2O2 OH-, and that's going to give rise to anti-Markovnikov hydration of the alkyne such that hydrogen adds to the more substituted carbon, OH to the less. This enol, you've got to recognize it's an enol. There's the ene, there's the ol. This enol, like all enols, will rapidly equilibrate to the corresponding carbonyl compound, which in this case is going to be an aldehyde. And there we have it. So we've seen in this chemistry of alkynes, whether it be a Markovnikov or an anti-Markovnikov hydration reaction, we've seen that we can convert alkynes into aldehydes and ketones through the intermediacy of these enol structures. It's not uncommon for students to list the enol as the final product as a result of either a Markovnikov or in this case an anti-Markovnikov hydration sequence, but you've got to recognize that you've got an enol that rapidly equilibrates to the corresponding aldehyde or ketone, and you need to show the aldehyde or ketone as the product. So I'm really talking about a predict the product type question here. So, for example, if you had this somewhat sophisticated alkyne, which is a terminal alkyne, and you were asked to show some products resulting from it. Let's say in the first case we had excess HBr. In the second case we had excess Cl2, molecular chlorine. In the third case we had a reaction with a mercury dication in the presence of aqueous acid. And in the final case, we have reaction with a hindered organoborane in the first step, followed by H2O2OH- in the second step. This is a classic predict the product type question. 4 different reactions. We've got to show the products in each case. So here we go. What happens under hydroboration conditions? This is a Markovnikov process. We're going to add hydrogen across the less substituted, bromine across the more substituted carbon. But when we do that, we form an alkene, and the alkene itself is subject to further reaction with HBr, especially since we've got excess HBr, so we do it again. Another equivalent of hydrogen across the less substituted, another equivalent of bromine across the more substituted. The result is we would form a geminal dihalide. And over here would simply be a methyl group. See, we started with a carbon attached to 1 hydrogen, but after 2 hydrohalogenations, we add a second and a third hydrogen, which ultimately just gives us a methyl group. Keep track of your carbon count here. It's very easy to lose track of the total number of carbons. We've got a benzene ring here, which if considered a substituent would be a phenyl substituent. So I've got a phenyl substituent off of carbon 4, and you want to make sure that that's still the case in your product. Carbon 1 is the carbon that picked up 2 hydrogens, so now it's a methyl group. Carbon 2 is the carbon that picked up 2 bromines. This is my geminal dibromide. Okay, very good. What about halogenation with chlorine? Well, you remember halogenation is a reaction which gives rise to an anti-vicinal dihalide if we react an alkene with chlorine or bromine. But in this case, since it's an alkyne and we're using excess chlorine, we're going to perform that reaction twice because once again, we have 2 pi bonds. So make sure you keep track of all of your carbons, 1, 2, 3, 4, 1, 2, 3, 4. The addition of chlorine in this case is going to take place across carbons 1 and 2. And so you are going to add chlorine twice. You're going to add molecular chlorine twice in order to give you a tetrahalide. And there's the hydrogen, that is that hydrogen right there, the hydrogen of the terminal alkyne. So these were older reactions, which we'd already covered in class, but in a predict product question like this, you might have to take the same alkyne in a lot of different directions, And that might include some of these new reactions here. What is this reaction with mercury 2+ under acidic conditions? Well, those are the conditions we utilize for a Markovnikov hydration of an alkyne, which means we're going to add H and OH across the less substituted and more substituted carbons respectively. When I add H across the less substituted carbons, that gives me essentially a methylene unit out here. Still one pi bond left over. And OH across the more highly substituted carbon, I have an enol, which I know will equilibrate to the corresponding ketone in this case. Keep track of where your carbons are. Make sure that you have them all present. 1, 2, 3, 4. Don't lose any carbons along the way. The enol equilibrates to the corresponding ketone. Once again, the pi bond moves from the carbon-carbon region of the molecule to the carbon-oxygen region of the molecule. There it is, keeping otherwise the carbon skeleton in place. 1, 2, 3, 4. This hydrogen atom of the enol, essentially migrates over to this carbon, formerly of this ene, to give you now a methyl group. And there's my ketone. And then finally, the last reaction here is an anti-Markovnikov hydration, very closely related to the one we just did, except that the H and the OH will add to different carbons. So my H is going to add to the more substituted carbon, the OH to the less substituted carbon. Once again, I have to recognize this is an enol, and it will rapidly equilibrate to the corresponding aldehyde or ketone. In this case, it's going to be an aldehyde. Keep track of your carbons. So going back to our starting structure, 1, 2, 3, 4 carbons, and then the phenyl substituent. In my case of my enol, 1, 2, 3, 4 carbons, and then the phenyl substituent. And then after equilibration to the corresponding aldehyde, it is still 1, 2, 3, 4 carbons, and then the phenyl substituent. So those are some predict the product type questions which utilize some of those alkyne reactions.